welcome. Today we will see some beautiful application of Parseval identity and Fourier series in general regarding a very interesting problem that is called the isoperimetric problem. What is an isoperimetric problem? So, in our school days in the basic calculus, we have learned that given a fixed perimeter among the rectangles, which rectangle can take the maximum area. So, for example, now if we have a rectangle which is perimeter is, let us say, 4. So, which I take so suppose this side is let me take 0.3. So, this is 0.3. So, this is 0.6. Now, this is 1.7 and 1.7. So, now and I take another, let us say the perimeter is 4, I take 1, 1, 1, 1, a square. So, what is the area of this? The area is 1, and what is the area? This is 1.7 into 0.3. So, this is 0.51. So, obviously, this area is bigger than this area of this rectangle, where their perimeter is same. So, with the basic calculus, one can always show that among such class of rectangles with a fixed area, let us say a fixed perimeter, let us say L, then the rectangle which takes the maximum area is square. That is a very easy, you can take x and then this perimeter, this is x x, and then this is L minus 2 x divided by 2, then area is a function of x. You apply your standard calculus and can get that this x is equal to L by 4, and that will give you a square. Similarly, among all triangles with the fixed perimeter, one can see that isosceles triangle, this encloses the maximum area. So, natural thing is to ask, so why only the triangle and the rectangle? Suppose for any general n-gons with the same perimeter, which geometric shape is going to give us the maximum area. And now, in the ancient Greek, they knew that given any closed curve, let us say I have a closed curve like this with the same perimeter, then which curve is going to encircle the maximum area. So, this in general, this type of problem is called isoperimetric problem, and which have been studied since ancient time, and the study still is going on in various directions. So, what we will see in this lecture is, first part will be discussing little bit about the historical account, I mean how this problem has progressed, and then we will give a very beautiful argument of Steiner. So, Steiner had produced various proof for this problem. So, we will discuss one of the proof, and then we will give a very rigorous proof using the Fourier series techniques. Okay, first let us have a story. In the Greek mythology, Dido was the founder and queen of Carthage, a city on the northern coast of Africa. She was the daughter of Belus, a king of Tyre in Phoenicia, and the sister of Pygmalion. King Belus has wanted his son and daughter to share royal power equally after his death. But Pygmalion seized the throne and murdered Dido's husband. Dido and her followers fled from Tyre, landing on the shores of North Africa. There a local ruler named Larbus agreed to sell Dido as much land as the skin of a bull could cover. I mean, one would like to imagine that only a very small patch of land a skin of bull can cover. However, Dido was very intelligent. What she did is that she cut the skin of the bull into very thin strips, so like thread. Then she faced, most likely solved, the problem of enclosing the largest possible area within a given perimeter, because when you were taking the thin strip, you are fixing the perimeter. Now, you tie from keep on tying it. So, you make a tie. So, this is going to be a closed curve. Now, she knew that how to put the closed curve, so such that she can get the maximum area, and that is what she did. So, natural intuition is that it is a circle. So, this is the problem then is the problem of enclosing the largest possible area within a given perimeter is called the isoperimetric problem in general. Okay, so, let us see some systematic development of this problem. The question: among all the figures of equal perimeter, which figure has the greatest area? That is what is our problem. Now, it was first realized that a square has greater area than long thin rectangle of the same perimeter. So, that is what we had already seen in our school days. The general question was investigated in the golden age of Greek geometry. So, Zenodorus, you can see that it is from 200 to 140 BC. So, what he showed that of all rectilinear figures having an equal perimeter, the greatest is that which has the most angles. And then Pappus, of all circular segment having the same circumference, the semicircle is the greatest. And geometrical approach could not go much further without the precise notion of perimeter and area. So, let us, before talking about the problem, let us start with Heron's problem. Let A and B are two given points on the same side of the line L. Find a point D on L such that the sum of the distance from A to D and from B to D is minimum. So, what is it saying? Suppose I take a line L here and I have A here, B here. Now, let me take a point D here. So, I have AD plus DB, and in another point if I am taking D prime here, this is AD prime, BD plus BD prime. So, I can keep on, I can choose this D double prime if I am choosing, then I have this. So, now is this AD plus BD, is it greater than AD double prime plus BD double prime, or for that matter AD plus BD is greater than AD prime plus BD prime. So, which means our job, the question is that does whether there exists a point on this line such that AD plus BD is going to be the least among all such sum of the length of AD prime plus BD prime. Okay, so here is the picture you can see. So, the proof is simple. So, now you take the line, you have the point A, you have the point B here. So, now what one do is that you extend the perpendicular to the line L and come up to B prime such that this is equal to this. Now, you join A B prime. So, where this is what you will get the point D. So, now you take any other point D prime. So, you have this. Now, let me call this as and then so AD plus BD. Now, my claim is that AD plus BD is less than AD prime plus BD prime. Okay. So, as we can see that AD prime plus D prime B is equal to AD prime plus D prime B prime, because this is an isosceles triangle, this is right angle. So, now you have got AD prime plus D prime B. Now, you look at the triangle AD prime B prime, this is the sum of these two sides. So, which means this is going to AD prime plus D prime B, this is strictly this is greater or equal to AB prime, sum of the two sides of the triangle is bigger than the third one. So, now this AB prime is nothing but AD plus DB prime, and now this is AD, because again BDB prime is an isosceles triangle. So, this is BD. So, this point D is going to give us that this is the minimum among the sum of these two. Okay. So, that is what the proof is. So, now next one is that if there exists a plane of n-gons having the largest area among all n-gons of given perimeter. So, here I am assuming that if there exists a plane n-gon having largest area among all n-gons of given perimeter, then it must have equal sides, which means it is a regular polygon n-gon. That is also not very hard to see, as you can see that. So, now let A1, A2, An be a maximal n-gon, then it has to be convex. Suppose this is very easy to suppose this is a n-gon, then if I am doing this length and this length, if I am reflecting this along this line, then this is the same perimeter. I am not changing the perimeter, but the area has increased. Hence, it has to be a convex region. Okay, let A1, A2 and A2, A3 be two adjacent sides such that A1, A2 is not equal to A2, A3. Suppose now I have A1, A2 and then this one is, this is A1, A2 and this is A3. So, which they do not, this is not A1, A2 is not equal to A2, A3. So, what we do is, so now you join the line A2, A3. So, now you draw a line parallel to A1, A2 passing through A2. Then as you can see by the previous observation, so you will get a point D for which the A1D plus A3D is minimum, and therefore, so I will draw the diagram here again, and so now let us see, this is my A1, A2 and this is A2, this is A1, A3. Now, and this is the line L, and now what I am going to get is that I will get a point D. D is this, if I by the Heron's problem, if I go, so if you join this, then this is my point D, and this D is different from A2. The area of triangle A1 DA3, this area of this triangle is equal to A1 A2 A3, because their height is same, the lines are parallel, but A1 plus A1 A2 plus A2 A3, this is greater or equal to A1 D plus A3 D. Now, construct the isosceles triangle. Suppose this is our alpha, this is our beta. So, now this is the parallel line. So, this is also becomes to beta, and this angle is alpha, and alpha is equal to beta. So, this is an isosceles triangle A1 A2 prime A3 such that A1 A2 plus A2 A3 is equal to A1 A2 prime plus A2 prime A3. So, now however, the delta of A1 A2 prime, the triangle area is bigger or equal to triangle A1 D of A3, and that is what is a contradiction. Okay. So, that is easy to see. In case of triangle, as we have seen, this is going to be equilateral, and in a quadrilateral, without having a rectangle, if I take any quadrilateral, then the maximum area is going to be attained by a rhombus. Okay. So, now that is the time when Steiner has entered in 1841. So, if gamma is a figure whose area is greater than that of any other figure of the same perimeter, then gamma is convex. That is trivial to observe, you can convince yourself. Suppose if it is not convex, then you just flip it along this line, what you are going to get, that this area, this entire thing is bigger than this green patch. So, therefore, it has to be convex. So, that is believable. Now, Steiner has to prove that this is a circle. So, now what he had proved, if gamma is a figure whose area is greater than any of other figure of the same perimeter, then gamma is a circle. So, here the figure is understood to be kind of a closed curve. So, now the proof of this is that if you divide, you can get a line. So, it is a convex domain. So, if you divide it, so along that, if you can see on one side of that is a semicircle, then you are done. Okay. So, now suppose it is not a semicircle, then what is going to happen, that you know that if it is a semicircle, you join any 2 points here, then this is going to be 90 degree. That is what the Euclidean geometry tells us in our school. So, now what happens, suppose it is not 90, now you take this. So, keep this 2 here. So, now this 2 here, now you stretch it up to 90 degree. Now, what you are going to, you are not changing the perimeter, because this is the this and this, they are the same, you are keeping as the 2 here, but the area has increased. So, therefore, it is, that is a simple geometric argument. Steiner said that this is going to be a semicircle. Now, there are lot of criticism came. So, first of all, what do we mean by a figure? That is obviously we are assuming there is a closed curve, and the interior of a simple closed curve or not, do we allow intersection. So, and then are we assuming for any simple closed curve the notion of length exists, because when we are talking about perimeter, we are talking about the concept of the length. So, now the question is that whether the length exists or not. Okay. And then most importantly, what Steiner assumed, that such a gamma exists. Look, what Steiner has proved. Steiner proved that given a fixed perimeter, if the curve is assuming the maximum area, then that has to be a circle. Now, what he is assuming, that there exists one such curve which assumes the maximum area. It may not happen that there exists such a curve. So, now even the criticism can be well understood in this simple example. One is the greatest integer. I can prove that, let n naught be the largest integer. There we are assuming that let this curve has the maximum area, then I am proving that this curve is a circle. So, now here among all the curves, among all the numbers, suppose if I am assuming that n naught be the largest integer, then n naught plus, if n naught is greater than 1, then n naught square, which is again an integer which is strictly greater than n naught, which is a contradiction. So, now that is the flaw in Steiner's argument, that he had tacitly assumed that such a curve exists. Then there was a real controversy came up, and which also include Dirichlet and other people with the Steiner. Then at a later part, so the first person who gave a full proof of this isoperimetric problem is Weierstrass. So, he, as a matter of fact, there was a proof that if you assume there is a curve which has among the same equal perimeter has the maximum area, then by using calculus of variation technique, Euler has proved that also another proof by using calculus of variation technique. As a matter of fact, he developed the calculus of variation to solve this problem. And then Weierstrass refined the proof of Euler, and he gave a full proof without assuming the fact that there exists, without assuming that such a maximal curve exists. So, then let us try to define all these things in a rigorous fashion. What is our problem? So, what do we mean by a curve? Now, curve is a continuous map from gamma from any interval to R 2. It closed means gamma of 0 is equal to gamma of 2 pi, and which means you start with any continuous curve, and then this it is starting point is the ending point, and the simple means it is 1 1, which means one is kind of discarding the curve like this. So, this is the just the simple curve which is 1 1. Okay. Now, let gamma s, I define the set gamma s equal to, this is a set in R 2 and which has all the points of the curve, which it means x s and y s, because there are two coordinates. Okay. And if both x and y, they are differentiable, we know that in our calculus course that the length of the curve can be, we say that if they are differentiable, it is rectifiable, and the length of the curve is integral from 0 to 2 pi mod of gamma prime s ds, which is equal to x 1 prime s square plus y 1 prime s square root, that is the modulus, Euclidean modulus ds. It exists and L is called the arc length of the curve. So, this is basic calculus what we had learned earlier. Now, so as we know that there exists, so every curve admits a parametrization by arc length. So, in which that is x 1 prime square plus y 1 prime square is equal to 1. So, we can consider always a parametrization by arc length. Okay. And then with the several variable calculus and with the exact differential, we know that A is equal to minus of 0 to 2 pi y s x prime of s ds, which is equal to 0 to 2 pi y prime s x s ds x plus ds. And if we add these two, then 2a is equal to this plus this. So, which is equal to a is equal to 1 half of 0 to 2 pi y prime s x s minus y s x prime s ds. So, this is the standard fact from the calculus, and this is very important to know that this is what our area is. And if we to be very careful, then y is of course a continuous function and x prime of s. So, now this has to be integrable. So, we can take a C 1 curve, that means x prime is also continuous, then the question of the integrability is no more a problem. Okay. So, now there comes Hurwitz. So, what was his proof of the theorem? So, the theorem of the Hurwitz, so he precisely said that suppose gamma is a simple closed curve in R 2 of length L, gamma is a simple closed curve with length L, and let A denote the area of the region enclosed by the curve. This is the area of the region which is enclosed by the curve, and I can take this. Suppose if I consider another curve or some other curve. So, now, so for this curve the L is fixed. Now, the area is going to change. Now, whatever the area you are going to take, the area will always be less or equal to L square by 2 pi. This is the perimeter, and as you can see, if L is 2 pi, then this 2 pi L, then this is 4 pi square L square. So, Hurwitz theorem states that suppose gamma is a simple closed curve in R square of length L and A denotes the area of the region enclosed by the curve, then A square is lesser equal to, here there is a typo, which is equal to 4 pi. So, now if our curve is a circle, then this would be, the length would be 2 pi r, and therefore, the L square is equal to 4 pi square r square, and then L square by 4 pi, this is equal to pi r square. So, which essentially tells that this is the circle, the area is equal to, equality holds if A is a circle. So, we will in the next lecture, we will prove this inequality. Thank you.